Good afternoon, everyone. So, I would like to thank you all for registering and taking time out on a Sunday to learn about building risk assessment, BRA approach with case study examples. And this is our 100th webinar in a series of technical webinars that we are conducting. As a practice, we are conducting one webinar every month. So please follow us on LinkedIn and YouTube and make sure to check our website for the latest updates. Today, we have an experienced panel of speakers. Like always, we have Mr. Ijazul Karim Rao, who's Managing Director and Principal Integrity and Safety Consultant, Madam Mubina Khatoon, she is Director Engineering Services. Then Mr. Anthony James William, who works as General Manager, Global Sales with us. Since this is a quite technical subject, we will touch only the key theoretical and practical aspects of building risk assessment. We will be going through the standards and regulations that are followed and applicable in this field. And then we will share a detailed case study overview. And at the end, as discussed before, we will have question and answer session. You can ask your queries. So let us begin. I will start by giving a brief introduction about Velosi and what we do. So Velosi is a leading global consultancy firm that provides asset integrity, HSE, engineering, environmental and software development solutions to the clients in oil and gas, petrochemical, gas and energy sectors around the world. We also have our in-house built proprietary software, which is a Whale Plant. It is an industry-leading SAP certified complete asset integrity solution that is currently being used by many oil and gas giants such as Dragon Oil, TANAP, ADNOC, and many more. Founded in 1982 in Malaysia, Velosi Group was acquired by Apple Spain in 2011. So by these numbers, you can estimate that we have been in the industry for more than 43 years so far. We have expanded our footprints to more than 86 countries and have so far completed more than 1,350 projects with 500 different clients around the world. We operate globally through our associate offices in Middle East, Africa, and Asia. Our corporate office is in UK, and head office is in UAE, Abu Dhabi. And we have associated offices in more than 86 countries worldwide, as discussed before. Our areas of expertise are asset integrity, management services, HSC, engineering services, software, and training.
Assalamu alaikum and good day, everyone. This is the, I think, 100th webinar in our series, and today's 100. We are completing webinars on the same way. And the title is Building Risk Assessment, which is BRA. And so good presence. I see 281 people now attending the webinar from various parts of the world. And it's basically appreciation for our effort to prepare this material and present to you in a detailed manner. As you know that our webinars are like not a shorter one. We spend 1.5 hour to 2 hour minimum and try to explain methodology with case study, with example, and we also have a Q&A sessions, and feel free to write your questions and we'll try to answer those questions at the end of the session. So one thing, like when we prepare these webinars, so we assume that there would be some young engineers who would be attending these webinars. There would be some medium level engineers, and there could be some experts also. So our main focus is on the young engineers. And if it's become boring for the senior engineers, so I apologize for that, because they might be getting a repeated information. But for young engineers, it's better to go with the full steps, and they should know all the details. So basically, building risk assessment is a tool used to evaluate the risk to the people in occupied building surrounding the process plants. If you see a process plant where we have a process area, utility area, tank farm, and there are building around that, administration building is there, control room is there, substations are there. So some are manned, some are unmanned. So if there might be any accident, God forbid, then whether the occupants of those buildings would be under danger or they would be safe. So this is the objective of building risk assessment. Evaluate building exposure to fire, explosion, and toxic risks, identifies hazards, model consequences, and define design mitigation measures. Then measure regulatory alignment and safeguards for people, asset, and operations. So, why is building risk assessment important? As I said, if a management team sitting in the administration building, and if that administration building is too close to the process plant, and the administration is required to take corrective or preventive action if any incident happened at the facility, if the administrative building or control room of the plant would be affected by the accident, then who would react to the accident? Who will manage the situation? Who will drive the emergency response plan? So that's why the building risk assessment is very important for the future, or like actions which are required to be taken post accident or during the accident at the plant. So that's why it is more important. So what BRA does, identify hazards at early stage, then we can take action to protect the building. We may also know like what consequences it may have in terms of losses. Then also how we can prevent those losses. Let's see like what are the examples from where we can learn the lessons, like if the building risk assessment could have minimized the losses or prevented the losses. In 2005, there was an explosion in BP Texas City refinery, which killed 15 people and injured 180 plus people. Buildings were placed dangerously close to the process unit and risk findings were ignored, leaving workers vulnerable to the accident. So in this, building like a sitting or building layout, then hazard analysis and audit follow-up. If those actions could have been done, then this accident could have been, like if accident was there, the losses could have been minimized. Basically, during like there was a shutdown, they placed like a container for the workers or for the contractors, and then there were temporary offices were made around the refinery, and that also increased the number of fatalities or injuries in the accident. Next one is Texaco exploration and production explosion in 1997, and explosion as Texaco Milford Haven refinery occurred inside a compressor building due to equipment failure and undetected gas leaks, causing fire and major damage to the building. If this building could have been checked for the like explosion loads and situations, then this problem could have been basically minimized. Yes, the preventive maintenance activities, the effective gas and fire and gas detection system, if that could have been implemented, so the incident might not have been caused. But if the incident was there, so then the secondary part is if the building could not collapse. So this was one of the lessons learned from this accident. There's another example, Phillips 66 Houston Chemical Complex explosion in 1989. A series of explosions occurred at Phillips Petroleum Company Houston Chemical Complex in Pasadena, Texas. And this was also like everything okay? So building and layout vulnerabilities caused contributed to the more losses. A robust BRA could have modeled vapor cloud formation and aggression scenarios, assessed building layout and spacing, which is blast resistance, separation, ventilation, and identified critical gaps in detection and fire protection system. This could have helped. But if those studies were not done in a proper way, so there are incidents. So these are the lessons learned from the previous incidents, and companies are now making a more robust like a BRA assessment, especially at ADNOC, like 3 studies like QRA, FERA, and BRA. QRA is quantitative risk assessment, FERA is fire and explosion risk assessment, and BRA is building risk assessment. Those 3 studies are part and parcel of every project. And also these studies are repeated after plants in operation every 5 years or so. So if we try to check to make you alert, so there's a first question if we have to ask, which of the following incidents could have been reduced or prevented with proper BRA? Number 1, building fire from gas leak, equipment damage from flammable vapors, structural collapse due to explosion, all of above. So what should be answered? Gentlemen, write in the chat box, question in the chat box, so we can see if you are awake and you are also understanding what is the subject being discussed. So please write down. So we see people are adding, mostly answer is right. The answer is D, all of above. Like if BRA could have been done, building fire from gas leak could be minimized, equipment damage from the flammable vapor could be minimized, structural collapse due to explosion could also be minimized or prevented. Now, here is a question where like somebody may say, why, Mr. Jaz, you are going to the basics. So it's the basic, simple. What is risk analysis? We all know that risk is a multiple of probability of failure, a likelihood of failure into the consequence of failure. And there are two methods, rather there are three methods. One is qualitative risk analysis method, then semi-quantitative risk assessment method, and then quantitative risk analysis method. So either of these methods can be used in the risk analysis. Here, how it was started, like in 1950s, there was some movement like used an alternative to market insurance. Insurance companies started using it. In 1970 to 1980, used derivative as a risk management instrument as the companies improved their financial risk management. Then 1980s, the oil and gas sector started using it practically. Then benefits like we can recognize and control hazard in a workplace, create awareness among the employees and people at large, establish risk management guidelines based on accepted safety procedures and regulatory requirements, detect, assess, and compare the total financial and organizational effect of the risk to the organization, decide the next action to eliminate security flaws and enhance security, identify security gaps, and determine the next step to eliminate security flaws. Then, in general, whether the risk assessment, whatever like a technique it could be, like a FERA, QRA, BRA, these 5 steps are almost common. Like first of all, we need to identify the hazards and risk. Then we analyze the risk like multiplying the probability of failure we assess, consequence failure we assess, and multiply both, we can get the risk. Then develop a risk management plan, like how if risk is there, whether it's being driven by probability of failure side or it's being driven by the consequence of failure, then how the controls or mitigation measure or preventing measure should be implemented. Then implement the risk management plan, then monitor the risk. These are the normal 5 steps in the risk assessment and management process. If you see in terms of dollars, so we have system definition, then hazard identification, consequences there, then likelihood of failure, then we get a risk. Normal fundamental definition. So I know that I'm repeating this for the youngsters, so you can understand the concept of risk. We try to understand risk in terms of cost. So it can be applied. An insurance company, we can take an example. The risk for the insurance company is the PUF and the CUF. Let's take an example. One insurance company insure 1,000 cars in UAE. Let's take an example. What premium of each car? They charge $1,500 per year per car. Okay. The total revenue of the company is like multiply 1,000 multiplied by 1,500, 1.5 million US dollars. Like if the number of accidents to the car in 1 year, let's say are 50. If it is a 50, then chance of accident like 50 over 100 is 0.05 per year, and price for each car is, let's say, $15,000. Then the cost what insurance company will end up paying 750, and there is a margin for 750. But if due to rainy season, the fog or some other reasons, if accident goes 100, then it would be a break even. But if the number of accidents goes more than 150, more than 100, then the insurance company will be making losses. That's why sometimes insurance companies get bankrupt. So this is the explanation of the how risk we can like associate with the number game in our mind. So the type of risk assessment, as I said earlier, qualitative and quantitative. Qualitative is morely judgmental based, like a team gathering. We get the idea what the probability of failure people may contribute, then what is the consequence, and then by assessment, what would be the risk position. Whereas quantitative mean there would be some numbers for the probability calculations, and there would be some numbers for the consequence calculations. And these numbers, when multiplied, you will get a quantitative risk number. So that is the difference between qualitative risk analysis and quantitative risk analysis. Then also demonstration of the qualitative risk assessment or semi-qualitative risk assessment. For example, a bow tie, this example of a bow tie, if you see here, like if there is an incident, why this incident, first it would be cost. Cost, for example, safety event, safety event, safety event, safety event, it could be like, for example, corrosion, maybe lack of basic like a safe design. There could be lack of maintenance, lack of right operations, and these are the causes. And this could be managed, prevented by better design, better operating instructions, better maintenance management system, and so on. And so as the leak or the release of material from the pipe does not occur. If it occurs, then it may have a serious consequences in terms of fire and explosion and fatalities. How we can prevent that? That can be prevented by fire and gas detection system, firefighting system, or by putting the burns on the tank sides and so on and so. So in this way, we can see how these hazards is first basically escalated or prevented, and how the consequence can be mitigated and prevented as well. So here, like there are, as I said earlier, there are various types of the risk assessment technique, what we use for the risk management of the facilities. Like first one is a QRA, which is quantitative risk assessment. ESA, emergency system survivability. Then there is a ERA, is a spelling error, evacuation, escape, and rescue analysis. Then FERA is the fire and explosion risk assessment. BRA is building risk assessment. So all these techniques are used to assess how the facilities are exposed to certain hazards and how those are contributed at terms of consequences and risk, and then how we should take the required preventive measures. Now, if we try to basically compare this normal comparison between these techniques, here BRA is the first, QRA and FERA. All three are the risk assessment. All three are the risk assessment, only final outcome is a little bit different. So we should remember it. BRA evaluate risk to the people in occupied building from a fire, explosion, or toxic release in the occupied building nearby. QRA quantified likelihood and consequence of hazardous events using measurable data. FERA is a focused study of fire and explosion hazards and their impacts on the plant, also on the neighboring plant. So FERA sometimes cover BRA part also. QRA sometimes also cover most part of BRA as well. The purpose of all the studies, the purpose of the BRA is to protect building occupants and recommended mitigations. Then to demonstrate facility in QRA, to demonstrate facility safety support, ALARP, and cost-effective safety decisions. FERA to identify, minimize fire explosion hazards and ensure risks are within ALARP. ALARP means as low as reasonably practicable. Then scope, narrow building occupants, then broad entire facility operation, then medium, basically like here the definition point of view, fire and explosion risk affecting asset and people relationship. May use QRA as a final stage, can integrate it with the FERA input also, use independently or within BRA and FERA, provide hazards data, feeding into BRA and QRA also. Then process, it is 3 stages, but like basically process wise, it is all the same. 5 processes are there. Like first hazard identification, then consequence modeling, detailed, like it should be detailed QRA or it should be BRA if needed. Not QRA, it's a BRA typo error, sorry. Then frequency and consequence analysis, compare against occupant acceptance criteria. Then FERA also hazard identification, fire explosion, modeling, risk evaluation. The process is more or less same. Output, BRA report with hazards, occupancy data, safety recommendation. Then numerical risk values, risk contour maps, ALARP justification. Then here recommendation for fire protection, then safe layouts and mitigation measures. Then application, assess safety of the occupied building, compliance with API RP 752. Then used across facility life cycle to justify safety decisions. Then FERA, basis for fire and explosion protection system, support BRA and QRA also. So this is a normal comparison. Like if you can have some idea. So easy thing is BRA is for the building, QRA is overall facility risk assessment, and FRA mostly focus on fire and explosion impact on the assets and the facilities. So standards, like there are many standards which could be referred, but we are just making you a little bit familiar, like ISO 3010, risk assessment technique and tools for hazards and risk evaluation is a common one. ALARP guidance is also there. NAP 101 is a life safety code requirement for building safety, fire protection, and the safe egress. This is important. NAP 30 is normal chemical hazards. Then this is the standard, which is a base standard. API RP 752, management of hazards associated with the location of the process plant and permanent buildings. Next, like ISO 15544 is a petroleum and natural gas industries offshore production installation requirements and guidelines for emergency response. For building, it would be applicable. Then API RP14J, recommended practice for design and hazard analysis for the offshore production facilities. Then API 14C, analysis and design installation and testing of the safety systems for offshore production facilities. API RP750 is the API, like it is the management of process hazards. Then is a very normal standard risk management guideline principles, ISO 31000. So these are the standards, and then also there is more standard like safety, if we have to take DNV safety or fast training software also is there. Then there is a yellow book, methods for calculating physical effects. Then purple book, guidance for quantitative risk assessment. So these are also these are the international standards. The 3 slides are there, and this presentation would be available on YouTube also for your further review and follow up after 1 week or so. Now, these are the standards. I'm not going through each because I mentioned front pages are also there, ALARP framework, then like life safety code, NAP 101, then the NAP 30 flammable and combustible liquid code. Then there's an index for the NAP like a 752, which is basically building protection point of view standard. Then ISO 15544. This is also like offshore production installation requirement for the guidelines for emergency response, as I mentioned earlier. 14J, which is recommended practice for design and hazard analysis of offshore production facilities. Then analysis, design, and installation and testing of safety systems for offshore production facilities. Then management of process hazards, which is API RP 750. Then risk management guidelines, 31,000. So there is a safety training manual from DNV. GL is the older one. Then here, this is a method for the calculation of physical effects, TNO standard. Yellow book and purple book, guideline for quantitative risk assessment. Then, no, there is an ADNOC standard also because we are mostly operating from Abu Dhabi. So the ADNOC got one of the best code of practice series for HSE management for each project. So we are also using them as one of the best practice being used by ADNOC in the region. So, for example, ST10 is a HSE basically management system QRA standard. Then ST06 is regarding basically control of major accidental hazard guideline or standard. Then there is also ST03, which is basically how to identify HAZID, INVID, and OHID, safety hazards, environmental hazards, and occupational health related hazards, how they should be identified in a workshop. ST03 basically provide the guidelines. Then HSE RM ST09, which is basically FERA guideline or standard. Then HSE RM ST07, this is ERA standard. There are the other standards that are also referred in these standards, which provide you quite good guideline how the international standard could be interpreted to make an easier use. So ADNOC has provided these standard guideline, which is more simplified and all steps are very clearly defined and people can use easily. So like this is the ST10, which is QRA standard. This is the basically control of major accidental hazard, ST06. This is basically for the INVID, OHID, and HAZID, like a workshop related guideline and standard. And this ST09 is related to FERA, fire and explosion risk assessment And this is basically ERA. There are similarly for ESA as well as for like other studies which are associated with the ADNOC guidelines. So now we start our BRA case study, right? So one thing I would like to clarify that like we have modified the data so as we don't reflect the actual situation of any facility. So it's a mix of a few studies. So if any information correlated with any one particular facility does not mean we are presenting the actual case. The actual case has been modified and practically distorted to hide the actual situation of the facility. So here HECI study scope was Velosi was appointed by the company to carry out HECIA for a project, including building risk assessment. An integral part of the HECIA process is to carry out building risk assessment study, which is developed in line with ADNOC COP. At that time, ADNOC COP it was older standard because study is older, V1-02 and V5-06. So objectives of HECIA study, like what it was like a compliance with HSE regulation and standards, like also major accidental prevention system should have been developed. Then health, safety, and environmental hazards should have been identified. Risk should be managed. On-site and off-site emergency plan should be prepared, and everything should be within the acceptable or ALARP region. Then, if you see the studies are almost 20. If you see here, so BRA is one of those, is including like HECIA workshop, like HAZID, INVIT, OIT, Bowtie, SIMOP, and ALARP. Then HECIA studies include HECIA screening report, HAZID, INVIT, and OIT register, HECMS review and analysis, EIA report, then PPC report, noise assessment study, H2S zoning report, QRA report, FERA report, BRA report, ERA report, ESA report, HEC critical activity register, HECS performance standard, COMA report, then action tracking register and HECIA report. This is the family for the HECIA. Then there are other studies additional like inherent safe design review, design HSE plan, noise allocation study, then FNG mapping, seal assessment and verification study, flare and venting, so vent dispersion study, toxic gas refuge impairment assessment, transport and traffic management plan, then deviation management register. So those were the all deliverable, what we delivered as a part of this project. But our today's focus is mainly on the BRA. So what is the BRA scope? Like we were supposed to carry out BRA study to cover these 8 buildings, including substation 1, substation 2, warehouse, maintenance workshop building, control room and office building, laboratory building, canteen, locker buildings, gate access buildings, truck loading shelter. So BRA execution steps, like how would they do? It's the same steps what we identified earlier also. It carries almost 10 steps, like hazard identification, process definition, isolatable section and parts counts, isolatable sections volume and mass estimation, congestion mapping, then release frequency, consequence analysis, risk modeling, design verification, and protection recommendations. So these are the basically 10 steps what are required as a execution of the BRA study. Deliverables. So BRA report, which covers normally terms of reference, methodology, consequence modeling, results, risk evaluation, recommendation, data tables, and figures. Supporting documents, risk matrices, plot plans, documentation of mitigation measures. Actionable information for stakeholders, awareness of risk compliance, improved building design. These are the basically deliverable for the BRA scope. Basic data requirement, what we need is basically the PFDs, P&IDs, heat and material balance, manning distribution philosophy on the buildings, then risk tolerability criteria, then applicable code and standards, and building occupancy data also. Process description, in this particular like study what we are referring to, the various units were involved in the process, like a fractionation unit, distillate like a unifying unit, Molex unit, PACOL unit, PAP unit, detail plus unit, nitrogen removal section, then utility system, jetty, terminal, truck loading station. Those are units were there as a part of the overall process facility. And name wise, we are not giving the overall name of the facility. So this is like a project location map. like where the facilities were supposed to be built. Approach point of view, we give more detail, like 10 steps are there, but those 10 steps are done in 3 stages. Stage 1 is basically a building and hazard identification. The stage 2 is building hazard evaluation, explosion hazard, toxic hazard, flammable cloud hazard, and fire hazard. Then risk management is the stage 3. So detail wise, it's like, as we said, like a building are identified by occupancy and functionality. This help highlight these needing further basically assessment. As per client required, all buildings will be assessed. Building from stage 1 will undergo further assessment. A consequence-based approach will be used. Focus on worst case credible scenarios. Then aim is to assess impact on buildings, including potential harm to occupants and the loss of functionality. Then stage 3, use a risk-based approach. This method is quantitative in nature. It considers both consequences and frequencies, and so on. Now here, if we try to see the people who are familiar with ADNOC deliverables, this is one of the flow chart. It starts with data collection, then we carry out HAZID, INVID, and OHID workshop, or focus on the BRA or QRA or FERA, start with the HAZID. Then HAZID workshop reports, there is a HAZID classification, MAH and non-MAH. MAH are further taken to the Bowtie, and Bowtie identify their various graphical representation of all the layer of protections, and then HECS identification, and then performance standards, and non-MAH we try to manage via HACMS. And for the MAH, the real HEC studies like ORA, EIA, air noise, then QRA, FERA, SAMO, MOPO, BRA, ISA, ERA, and finally COMA report is compiled. Sorry. Here, this is like how a COMA report look like. Here, if you say major accident hazard MAH identification from the HAZID workshop, then major accidental hazards MAH assessment studies, which are the QRA, BRA, FERA, ISA, ERA, and H2S zoning. Then HECS register, then feed stage design, detailed engineering stage design, operation phase. So we have to identify HECS for all the stages of the plant. Then if once these all risk assessment studies are done, we need to demonstrate whether all the operations would be in the ALARP region. Then emergency response plan is the last thing to be prepared as a part of COM. Here, building and hazard identification. So the HAZID workshop, we try to cover like a term of reference, then pre-populated HAZID workshop. We have a HAZOP session, HAZID session, and then HAZID worksheet workshop reports is prepared. So like HAZID individual, normally what we do, like it's a workshop, and where we team of various experts sit together, multidisciplinary team, and they try to think like what hazards could be there. Then accordingly, those hazards, their safeguards, their consequences, their current risk assessment, the future recommendation, and then residual risk all are assessed. So like here, for example, loss of containment from the fuel gas system, loss of containment from storage tanks, loss of containment from benzene, or the various process units which were involved. So all those hazards are assessed one by one. Then INVID workshop will identify air quality impacts, then also impacts on the soil and groundwater, right? So these aspects are based on their plant locations and operations are assessed. Whether those would remain within acceptable range, this is also checked. Then occupational health point of view, the health effect due to the inhalation of the toxic gas, including H2S, the health effect due to presence of carcinogenic, the items which can create cancer aspects, those are also assessed. OID workshop report consider medium and low risk health and hazards. So here, the identification of the buildings, these are the buildings where category wise, B5, B4, the type of the occupancy of the building and their heights. These are 8 buildings what we are assessing. So buildings locations are shown into certain area. Then the hazards which were identified as a part of HAZID workshop, high risk hazards were 15, medium high risk hazards were 26, low risk hazards were 0. And this is the HAZID worksheet, if you want to just a reference. So this is not the subject, but I showed you like you can have the full process of the system. Then, like a first thing, what we do after HAZID, when you start BRA study, QRA study, or FERA. So in general, like if I may tell you, like in Velosi, when we have to do these three studies, first of all, we try to do FERA. Then the same information is carried forward for QRA, and the same information is carried forward to BRA. So basically, there are common steps like isolatable sections. These isolatable sections are marked on the PNIDs with the help of the ESD valves, and then also remotely operated control like a motorized operation valve. They could be closed by automated action. Then normally and lock close valves, or there could also be isolation by the pumps and compressor bodies. Then these isolatable sections are shown like as a some data is got changed here because we didn't want to show the actual data. So where various isolatable sections are marked. And how they are marked? They are marked on the PNIDs. If you can see here, you can see color-wise. There are one isolatable section. Here we can see one and two isolatable sections. Like inventory groups, if people who are familiar with RBI concept, like if any leak or rupture would occur, then till the isolation is done, how much volume would be coming out? That would be driven by one isolatable section, or in RBI we call it inventory group. So then from each isolatable section, we have to see the probability of leak, like how many flange joints are there. Like normally leak will occur from the flanges, and then secondary leak may also occur due to like a corrosion, like if the hole is there in the body of the pipe or body of the vessel. So here, so we try to count all those like a flange, manual valve, instrument connection, pressure vessel with connection 50 to 150, with connection greater than 150, then centrifugal pumps and piping length. So in this, we try to find the parts count methodology and leak size distribution. Then we try to see like what kind of potential hole could be there, 1 to 10 mm, 10 to 50 mm, 50 to 150 mm, greater than 150 mm, or rupture. Then piping size leak for full bore rupture also is considered. Then input sheet, a source a term modeling, inventory calculation, like the when we have to import data into the software, so we have to like a SPETI and the fast software. So we need to estimate the volume of each isolatable section with its composition, with the operating condition, what we take from the heat and material balance of the basically process flow diagram, PFD. So that information is updated, and we calculated what is the volume based on the specific gravity in the heat and material balance, what mass flow rate would be there. Then accordingly, that data would be used by the software for the consequence calculations using Bernoulli's equation and thermodynamics equations, or the reaction kinetics equations. These are the three equations. Number one, Bernoulli's equation for the dispersion. Then thermodynamics also, there's an effect. And then reaction, heat of reactions is taken for the basically fire and explosion. So these three type of equations are used for the calculations by the SPETI and fast software. Here, input sheet, source term modeling, inventory calculation, like a well type, like when we say like if the flow would be like once system is taken in, there are two kind of volume. One is a static volume, other one is dynamic volume. Static is the like length of the vessel, diameter of the vessel, you can get the volume. Pipes, their diameter and length, we can get the volume. That is the sum of all those volumes can give you the static volume. Then if the incoming fluid is coming from the upstream side, then how long it will take to close the ESD valve? 2 minutes. If it is a remotely operated valve by operator intervention, then 10 minutes. So then we see that how big would be the consequences by the, like if there would be leakage or rupture with the help, like which would be contributed by the static volume as well as the dynamic volume of the fluid. This is a little complicated calculation, but if we do that, it can easily be done. It's done step by step. Then input sheet and source term modeling, inventory calculation. This is the sheet, like sectionalization of the plant or inventory groups, and then accordingly release inventory calculations, which are calculated and filled in the template. Then failure frequency is estimation is done based on the parts count. Like the total failure frequency of the one isolated section is a count of type of equipment, PUF and count of equipment, and the PUF and each type. The frequency of the loss of containment for each leak source shall be taken from a validated industry database and combined with the parts count to generate the failure frequency of the leaks from each section. Then parts count methodology shall be adopted in compliance with equipment failure frequency database as prescribed in IOGP 434-1 standards. The failure frequency of each isolated section shall be calculated as below as a combined calculation. Then example of failure frequency, like if there is a parts various like isolatable sections and they're small, like 3 to 10, this is the failure frequency. Medium 10 to 50 mm, this is the failure frequency. Large 50 to 150, this is the failure frequency. Then full rupture is this failure frequency. Right. Then consequence result assessment criteria, like when the BRA modeling, following result would be extracted from the FAST software: jet fire, flash fire, vapor cloud explosion. So these are the basically the criteria what we have to use for the acceptance or the vulnerability aspects as well. Now, risk calculation and assessment criteria. Here, from the BRA modeling, following result will be extracted from the security software: location-specific individual risk, LSIR, then land use planning criteria, individual risk per annum, IRPA, individual risk per annum, IRPA, risk tolerability criteria, then societal risk, FN curve, outside boundary of the project, societal criteria, which is normally plays role for the BRA side. Then we have to see the ALARP. Like everything, we cannot bring in the very acceptance limit, which is like if we try to bring this level of risk acceptance criteria, then project cost will go very high. And unacceptable region, we cannot operate the plant because there would be risk of fire and explosion. So we need to operate the plant within ALARP, which is called like as reasonably as practicable. Right. Then this is a basically FN curve, like if the plant will acceptable range, ALARP, and unacceptable range. So we need to keep the facilities under this range. Then land use risk tolerability is also there, like a plant, inner zone, middle zone, outer zone, and unclassified zone. Like these are the basically location specific individual risk acceptance criteria, LSIR. So if we see the plant, like this would be the inner zone, middle zone, outer zone, and wherever the buildings would be coming, those would also be shown here. So this was the like building hazard identification methodology, what I showed you. The same methodology basically is modeled and used. Then BRA assumption register, for example, hazard identification, isolatable sections, process parameters, inventory assessment, calculation methods, then release, direction and height of the storage vessels, human vulnerability, plant and structural vulnerability. Then we got aggression probabilities with UCOA, like a correlation model, risk ranking points, Manning distribution philosophy, detection and isolation philosophy, regulatory risk tolerable criteria. So these are the assumptions what we would be normally is taken into account while doing the modeling. But one thing, as I said earlier, if QRA is done, right, then FERA is done, then most of this information is already available, and we make a reference of QRA or a FERA study, and then BRA can easily be done with the simplest steps. Then FAST-50 software demo, like this is the like if anybody would be using it, so I thought that we should also show you the FAST-50. It's the DNV software we are using as a license, right, and perpetual license, and credit goes to them, right? So here, like how the screens start, like their various legends are there, how the information should be arranged, like plot plan can be brought into, then isolatable sections, like basically those are brought into with composition and fluids. Then basically after plotting the like the isolatable section on the plot, which is I think not shown here, we try to run the section placement, which is basically here. There should be certain like ball points or where or dots where we're showing the. This is not shown in this picture, so this is one missing item. Then the data of each basically isolatable section we try to fill in. Then here insertion of ignition sources, like wherever ignition sources would be coming, the input data in the Safety Fast software. Then marking your risk ranking points like receptors, where we want to see where the risk point would be acceptable or will not be acceptable, where the accidents would be taking place within the acceptable range or out of acceptable range. So these are the risk ranking points, like if we have to see the building, how the risk ranking point would be shown. So this is how the software output comes in. Then define consequence impact criteria. This is also given into the software. And then final modeling template, where all the isolatable sections and their plant layouts, they are shown. The data is mixed so as we don't give the right picture. So now this was the methodology. We have done identification of the hazard at the first place. Then we are going to stage 2 and 3, building hazard risk evaluation, consequence risk assessment part. So here, if you see that the first stage, what we did earlier is estimation of the inventory volume, selection of the consequence range of the hole size that we showed in the software, then consequence area modeling, then frequency analysis, ignition probabilities, risk modeling, building impairment criteria, overpressure damage effects. Like this is the isolatable section of this particular facility. Like one example only, there were hundreds of the P&IDs involved. We are just showing one here. Then this is the estimation of the inventory volume calculation. We are showing you the project what we are referring here. Then selection of the consequence range of the hole sizes, like from 5 mm to rupture. Then here, consequence area modeling. We use SWETI 8.11 with TNO multi-energy model, input source 3D model, plant and the equipment layout, potential explosion sites, then congestion criteria and output. These are the all steps done. Then congested area modeling, which is done as per the plant facilities, like the columns, the pipe racks, and which could be occurring as a hindrance to the any fluid release from the any leakage or rupture. So here is the congested area modeling, like ignition energy, obstruction, parallel plan containment, confinement, and multi-energy unconfined area and class. Here, like we try to calculate volume blockage ratio, volume of obstruction, and total volume. The PS is the potential explosion sites, where how much liquid will come and how much would be obstructed, and then the dispersion area or the contours would be affected by this data. So consequence risk assessment, like here the parts count for the leakage frequencies, then equipment, valve, instrument, all are accounted as I showed you in the previous section of the slides. So we calculated all the parts count and their failure frequency and also ignition frequency. Then total ignition probability, then ignition probability is taken from the data source, application to facility, and delayed ignitions, which is flash fire, 40%, explosion, 60%. Then ignition probability, normally we use the event tree, for example, accidental release, ignite, yes, then jet fire or pool fire. Then no ignite in the early phase, then dispersion cloud. Then delayed ignite, yes, no, yes, congestion confinement, no mean flammable gas dispersion. And there would be like a congestion and confinement, like a flash fire, no, and we see like a vapor cloud explosion, yes. So this way, this fault tree is followed by the software. Here, risk modeling, we use SWETI software, leak size consideration, then fire and gas detection system, there's a positive contribution, emergency inventory isolation valve, there's a positive contribution toward the risk reduction point of view. Then design criteria. The buildings are required to protect occupants and maintain functionality against explosion hazards expected to occur at a frequency of 10⁻⁻⁴ events per year. Then similarly, the overpressure assessment building will also be assessed against the 1/10⁻⁴ per year contours for explosion overpressure. Then accidents curves will be developed for all relevant buildings to determine side-on overpressures, impulse levels at various frequency levels. Then thermal radiation assessment, which also risk level would be considered, probability would be considered 10⁻⁴ per year contour for 37.5 kilowatt per meter square. It will consider the jet fire, pool fire, and flash fires. Then building impairment criteria like outdoor exposure, heat radiation, overpressure. These are the criteria. Duration of the fire 60 minutes, less than 15 minutes, 50 to 150 minutes, and 50 to 150 minutes. So overpressure damage effect, like if any pressure caused by the explosion, you cross more than these limits, then it can have a problem for the building. Here, like for example, like 0.414 millibar, it is an annoying noise. Then if 0.24 millibar is occasional breaking of the large glass windows. Then if 0.28 loud noise can take place. Then 0.69 breakage of small windows. If the pressure would be becoming 1.03 millibar, then typical pressure for glass breakage. 2.76 limited minor structural damage, but 17.2 50% destruction of the brick work of houses can take place. This is like a effect on the pressure caused by any fire explosion in the plant. Then BRA results, consequence results. So this is like now I'm showing you the output of the like a software, and the many things are done calculation point of view by the software. So I'm explaining how the process is working, how it can be done. I know that within 2 hours I cannot make like people BRA expert, but you are getting some idea like how the BRA, building risk assessment, or QRA, quantitative risk assessment, or FERA, fire and explosion risk assessment system works. So here, tool used consequence scenario modeled in DNV SVT risk using event tree analysis, failure frequencies, then result used for consequence magnitude estimation, sitting, layout, and design review, then contingency and planning of the safety measures. So here, what are the risks available? Jet fire could occur, pool fire could occur, flash fire could occur, overpressure explosion could occur. And now we have to see against all four, which is modeled by the software, like how it would be working. For example, here, like a jet fire, worst case scenario, thermal radiation level analyzed, result of all other isolatable sections are provided. Like if you see here, jet flame length calculated, worst case also the longest flame and highest thermal impact calculated. If you see here, this is the one isolatable section, IS-15A, the hole size 40, weather class 1.5D, jet fire length is 60.84, and jet fire thermal radiations with the vary 4 kilowatt to 12.5 kilowatt, 37.5 kilowatt, and 250 kilowatt. 250 kilowatt per square meter is a 62 meter distance, right? And this is 79 meter. Then this is the 99. So here jet fire length is 60.84. This is calculated by the software. Then here is the early pool fire if is there. Then hole size 40, weather class 5D, pool diameter 27.17 meter, and then pool fire thermal radiation effects you can see which area it would be. Like 142 is a 4 kilowatt, and 250 is not applicable, 37.5 is also not applicable. And here if you can see that these are the categories shown by the basically contours, and these are the like isolatable other sections. These are the isolatable section marked. Then pool fire, the radiation level, this is the range. Early pool fire, the IS-15A, 40 mm, 5D weather, largest fire diameter. Then late pool fire, then ignition of flammable material, pool fire diameter, and thermal radiation level modeled. So here, if you see that these all contours are provided by the software, and we can see where the pool fire impacts are coming, whether our building would be in the safe zone or out of the force zone. If you see here, our buildings are here, the one corner of the building being affected here, if you see this. Then here, the worst case scenario, the flash fire distance analyzed for LFL or LFL 50%, then worst case for the IS 35, 36, 25 mm hole, worst flammable clouds from N-pentane and isooctane and desorbent storage tanks were affecting things. And here the hole size 25 mm, weather class 1.5F, LFL 202 is basically meters, and LFL 50 416 meters. See the contour is going quite fast. This is the worst case scenario again. Now BRA risk analysis results. Here same, we have to see the This section presents the risk contours. That was the consequence. Before, first one is, let me show back so you can idea. Consequence result. Consequence mean if something will go wrong, what is the effect? But when we go to risk mean, risk is a multiple of consequence into the probability of happening. It means the risk result would be, the contour would be shortened. Here, the same thing. The section presents the risk contours of thermal radiation and explosion overpressure in order to determine the impact on the building identified. Then next, the results used for like a risk assessment to evaluate hazards, help identify potential on-site, off-site effects, supports decision-making for the risk mitigation. Then risk contours assessed for thermal radiation effects, jet and pool fires. You can see jet fire again, pool fire here, overpressure and the flash fire and toxic gas contours. Just to show you the risk, you can understand this kind of fire can be there. Here, these are the contours. Like if you see that thermal radiation at 1 into 10 raised to minus 4 frequency per year risk contour arising from jet fires. This is the area where you can see the various contours are coming in. The no manned and unmanned stations are impaired through the jet fires impingement and radiation directly. Whereas here, pool fire escalation analysis is shown in the above figure where the thermal radiation contours are not reaching other manned and unmanned buildings. So if there would be reaching to unmanned building, the building has to be moved away. Here, overpressure contours, if you see the explosion frequency contour provided show no manned and unmanned stations are basically impaired, not considered for future evaluation. This is basically the result which came for the overpressure due to any explosion. Then flash fire and toxic gas dispersion contours. Here, if you see, these are the contours, different colors, right? Both sides. Here, the flash fire LFL risk at 1 into 10 raised to minus 4 frequency per year contours is completely engulfing all unmanned and manned basically stations here. Engulf the problems are is reaching there. Then toxic risk impact with 10 raised to minus 4 frequency event per year is only affecting substation number 2, which is an unmanned building. Okay. Flash fire and this is toxic. BR result accidents curve. So here, overpressure accidents, thermal radiation accidents, where the target is being crossed. Here, this section present the risk contours for thermal radiations and explosion overpressure in order to determine the impact on the building identified. Then results used for risk assessment to evaluate hazards, help identify potential on-site and off-site effects, supports decision making for the risk mitigation. These are the basically accidents curves. If you see that, evaluate peak overpressure on all manned and unmanned buildings, identify building under imminent threat from the explosion hazard, use 1 into 10 raised to minus 4 frequency event per year as the accidents criteria, help prioritizing risk mitigation measures for the critical buildings. Here, overpressure accidents to all and impulse accidents for all buildings, you can see. Here, peak site on overpressure accidents frequency 10 raised to minus 4. If you can see, these are the buildings, peak site, pressure, overpressure, impulse, and impulse duration. This is the data which was produced by the software. Now, thermal radiation accidents for all buildings, the assessed thermal radiation effects at various intensities, then identifies high risk area like truck loading, substation, and warehouse. No building exceeds 250 kilowatt meter square radiation intensity at a given frequency. Result supports emergency planning and layout design for the layout facilities. So now, if you say BRA result escalation analysis, like how escalation can take place. For example, if there is a delayed basically fire and then more aspects are being contributed by the additional release or the if ESD system is not closed and then flow continue to come into the fire and contributing for more explosion and the continued fire. Then isolatable section IS-40 liquid pool separate and IS-48 we have considered for the thermal radiation. Here, thermal radiation impact 37.5 kilowatt per meter square thermal radiation effects truck loading shelter, substation 02, and part of the warehouse or the maintenance workshop. Whereas 250 kilowatt per meter square radiation does not impact any building, excluded from further assessment. Here, isolated section IS 48, transport process unit, product from tank farm area to jetty up to location. Large leak size 65 mm and high failure frequency, like a significant thermal radiation risk. Conclusion: critical areas identify for risk mitigation due to persistent thermal radiation exposure in that particular IS 48 isolatable section area. Then pool fire. Leakage can form a pool up to 89 meters in a diameter. Ignition leads to 37.5 kilowatt per meter square radiation, impacting building beyond impairment criteria duration. Then ALARP demonstration, which is done as a part of the last stage of the study. Here, regulatory requirement, mitigation approach, pool spread reduction, which is important here. The pool diameter reduced from 89 meter to 56 after bunt implementation, like dikes were made in that particular area. Then effectiveness, the bunt effectively limit the thermal radiation impact, reducing the risk to the acceptable level. Then thermal radiation control, 250 kilowatt meter square contour no longer generated, 37.5 kilowatt per meter square contour reduced, no longer affecting the building because we added the dike in between. So here, if you see the regulatory requirement, company code basically mandate identifying and preventing major accident hazard, limiting consequence to an ALARP region. Then physical modeling conducted by introducing a pump area with IS 48 isolatable section and secondary containment bunt were recommended. Here, like isolated section 48 liquid pool separate with bunt and like a thermal radiation after burn, so it was reduced to the acceptable limit. That this is the basically the ALARP demonstration. Like if we do that recommendation, then risk would be within the acceptable range. Conclusion recommendation. Here, like if we say overpressure impacts leak, peak overpressure, highest side on overpressure of 0.04 bar at the risk like probability 1 10 to the power -4 event frequency at substation 02. Then impulse duration 96.92 meter recorded at substation 02. Then design requirement, no additional blast resilience or resistance design required. Number 2, next is other buildings, 96.92 meter recorded at substation 02. Glass safety, laminated glass needed to protect occupants from the glass fragments. Then radiation intensity, the thermal radiation of 37.5 kilowatt per meter square at 10 to the power -4 event frequency. Then full impact truck loading shelter completely engulfed. Then duration concern radiation lots lasts longer than the impairment duration specified for the building. The radiation lasts longer than the impairment. Okay. Then source identified like IS 48 isolatable section, transporting process unit, products identified as a cause for the high radiation. Now recommendation, secondary containment bunt shall be installed for 3 pumps areas separately near the storage tanks to limit leakage of the flammable material from the spreading into large pool size fire. Similarly, canteen and locker room shall be provided with the flammable and toxic gas ingress protection, like air intake damper close on flammable or toxic gas detection outside the building areas. So we completed our like a discussion, like it went like very fast, but I was just going through my presentation and slides. I hope some message is conveyed. You're familiar like how this BRA system works. BRA is a building risk assessment, and it is similar to QRA and FERA, only technique wise is same, but the focus of BRA is to assess the risk on the occupant of the nearby building in the plants. This is the purpose of BRA. Whereas the purpose of FERA is to fire and explosion for the asset and facilities. With the QRA, helps to identify quantitative risks at the various location of the plant. Now, just to check your memory, guys, wake up. Like we are also going to the last part of the presentation. Then we will have a question answer session, and we will be able to conclude the today's session. So next question, please try to fill your answers in the chat box so we can see which is one of the three main stages of BRA. There are three stages in BRA. I just referred. Here A is hazard identification, then C is detailed risk analysis, B is consequence modeling, and D is project cost estimation, which is not one of the three main stages, which is not one of the three stages. One is not. So, okay, people are answering. Some are right, some are wrong. Which is not? This is the question. Sorry, I did not write the first question proper. Which is not one of the three main stages of BRA? Hazard identification, B, consequence modeling, 3, detailed risk assessment. 3 are there. The project cost estimation, not there. This is not part of BRA. Next question. Check your, if I'm able to convey some message, otherwise, okay, I spend my time, but whether it's helpful to you. Which of the following hazards is not typically assessed in BRA? Which of the following hazards is not typically assessed in a BRA? Fire and thermal radiation from the hydrocarbon release. B, long-term structural fatigue from equipment vibration. C, explosion overpressure from gas cloud. D, toxic dispersion of the hazardous chemical. So, guys, give your best guess. Mostly right. Mostly right. It is a B. Long-term structural fatigue is not covered under BRA. Next question. Which factor is the most important BRA when sitting occupied building near process unit? Which factor is most important in BRA when sitting occupied buildings near process unit? Office space utilization A, ventilation for comfort B, explosion overpressure and fire exposure C, ease of maintenance success. So this is a little bit difficult question. Which factor is one only out of four is the most important in BRA when sitting occupied building near process unit? Office space utilization A, ventilation of the comfort B, explosion overpressure and fire exposure. Yes, mostly right. Answer is right. And D, ease of maintenance success. The answer is C. So now three questions we try to answer. There are two more. Let me ask those two also. We can quickly ask. Two more are there. One more question. Two more questions. What is the primary regulatory equipment addressed? What is primary regulatory equipment addressed in ALARP demonstration? Like, what is the primary regulatory requirement addressed in this ALARP demonstration? This was the last question. It could be a little difficult. The installation of fire sprinkler in all buildings, evacuation drill for all staff, identification and prevention of major hazards, and demonstrate ALARP, daily monitoring of pump area pressure. Answer coming mostly right. The answer is B. In ALARP, we try to see identification and prevention of major hazards and demonstrate ALARP. Last question of the exercise. Which building features can reduce risk but cannot replace proper sitting? Which building feature can reduce risk but cannot replace proper sitting? Number 1, A, distance from hazard. B, location outside hazard zone. Number C, adequate spacing from other building. D, blast resistance wall and reinforced windows. Which building feature can reduce risk but cannot replace proper sitting? Distance from the hazard? Answer coming? It is a difficult question. Different answers are coming. So, which building feature can reduce risk but cannot replace proper sitting? Distance from the hazard? Location outside hazard zones? Adequate spacing from other building? Blast resistance walls and reinforced windows? Should be last one. D is the answer. So, we reached to the last stage. Still 283 people are attending the session. It reached to peak at 310. So we are happy to see your presence. Now, last part of our session, that is the question answers. Mr. Abdullah and Thomas, can you please help me to take the questions, and so as we can answer a few questions and we can call the day.
I am so impressed with the lecture. It was very, very clear and sound. But my question is, how can radiation risk map be used to identify areas requiring an immediate intervention? That's my question.
Yes, there are 4 type of fires are there, if you can see that, right? Like if I can go back to the presentation, there are 4 type of fires you can see in the beginning risk point of view. Like here, let me go a little back. So here, jet fire, pool fire, overpressure, and flash fire. When say radiation, radiation will come from the pool fire or flash fire. Jet fire will directly impact. So here, what we try to see, if we go to the consequence side, would be a little more better here. So this is the overpressure, this is the flash fire, this is the late pool fire, this is the early pool fire, and this is the jet fire. So now here, if you see, acceptance criteria point of view, if the radiation heat is not exceeding that, and then we have to see the contours, if you see various lines, and if our building is coming outside that zone, that would be considered acceptable. Otherwise, we need to take the corrective action. Either we have to reduce the consequence in terms of radiation or in terms of jet fire, whatever it would be, or we have to move the building away from the location. Okay, sir?
If kindly you can repeat the previous slide, like the types of the fire, how they
Yes,
impact the building.
yeah, you can say these are type of the fires, yeah, 4. And overpressure explosion also.
Yes.
Jet fire, pool fire, flash fire, and overpressure explosion. These are consequence related here.
Okay.
And now here, the question is if your accidents curve is reaching to the receptor, right, then we need to take the corrective action because we cannot expose a recepting point or building to exceed the limit of the acceptable criteria. So in this particular case, the worst case was like one particular isolatable section or portion of the plant or the tank farm area, which was causing a flash fire and then a pool fire, both combination, and then exceeding the acceptable criteria. So by putting the bund in between, the flash area could be reduced. That's the recommendation given.
Yeah, okay. Thank you very much for giving me this platform. And I must say, I am very, very much pleased with your presentation. And my questions, I have some quite number of questions that I have to ask. The first question is, what expertise does one need to be qualified for checking BRA? Do they undergo specific trainings and requirements? And my second question is, so if I am understanding clearly, does the software predict the percentage of risk in the building? And if there is a software for detection of risk, is there any device that houses such software? If there is, then what is the device? So again, what accessories are into the buildings for determining risk? Thank you very much.
Sir, there are 3 questions, right? First thing is like the person who would be doing BRA should have a training experience and should work under supervision of the experienced people. And the party or person who would be checking the report coming from the consultant, he should also have a similar training and experience as he can challenge. Otherwise, like there could be maybe wrong input data or garbage in, garbage out, which may come out of the software. That is the threat in between. Now, going back to the second part, like what the process is. So here we are trying to model the plant section by section of the plant. We call it isolatable sections, like which are placed as per the plant layout, right? And then we try to explode or fire, like whatever like a release will take place, first dispersion, then there could be immediate fire, there could be a delayed fire, then there could be a jet fire, pool fire, or a flash fire, depending upon the fluid or the content of that particular isolatable section or parts of the plant. Then as the spread is there, first we see the consequence with the immediate ignition or delayed ignition or explosion. And similarly, when we multiply it with the frequency like 10 to the power -4, then we see also the impact in terms of risk as well. So now the first thing is you try to take away the building. If the consequence wise, if the dispersion model is telling you whether the heat or the jet fire or the toxic gases are reaching to the building should be moved away, or the consequence volume should be reduced by putting dike or by making the isolatable section smaller. So this is like a detailed assessment. The main purpose of this assessment is to make the building safe. If building is coming nearby, then what are the corrective actions or preventive actions? Number one, like a control room or a substation, where manned substation coming near to plant, where you don't have any other option. So we try to make the building blast proof, like the walls would be very, very thick, right? Number two, all the glass windows would be made in a way just like a bomb proof. Like if any explosion takes place, it should not affect the building. Similarly, if there is a possibility of any ingress of toxic gases, so the in case of any detection of toxic gas nearby the HVAC intake, all the the intake of the HVAC system should be closed. So these are the corrective actions normally you take for while doing this BRA, and after effects of the BRA study or recommendation of the BRA study, how those should be implemented. Okay, sir. Yes. Thank you very much, everyone. And we look forward to meeting you for the next webinar, and that would be on FERA, like a fire explosion and risk assessment. So we are completing the series of webinar. We did before earlier QRA, then we did ERA, then we did ESA. Now we completed BRA. Next webinar would be FERA, like a fire and explosion risk assessment approach and detailed methodology. The content more or less would follow the same pattern, but outcome and the result would be a little bit different than BRA. Thank you very much, everyone, for attending this webinar, and we look forward to your feedback and comments. And this webinar would be available on the YouTube also in the coming week, and you can also download from there. Thank you very much and have a nice day. Bye-bye.